speakers know the order. We're going to start with Giulia, Kate, Praneeth, and then Zach. So if Giulia wants to start setting up. All the speakers in this session are incredibly accomplished, but I don't have a lot of time to tell you about all of their accomplishments. So what I'm going to do is to briefly just tell you where they're coming from and what their interests are. And what we'll do also is while we are taking questions for one talk, I'll ask the next speaker to come to the front and start setting up. Okay, so our first speaker is Giulia Fanti. She is an assistant professor of EC at Carnegie Mellon University. And she has a lot of different interests that are related to our workshop, including an algorithmic foundations of blockchains, distributed systems generally, privacy-preserving technology, and machine learning. And we're going to start with her.
Thanks so much, Nika. So today I'm going to talk to you about a distribution-centric perspective on data selection for federated learning. A lot of topics that I'm interested about for this workshop. I decided to focus on this one. And this was work with a number of talented collaborators. So when FL was first introduced, so Katrina gave a great setup here. When FL was first introduced, the pipeline that people typically talked about was that we would have this data from multiple distributed clients, and we would train a model that was randomly initialized and export the federated computation to the client devices. With time, our models have been growing bigger and more complicated, and there's started being benefits to pre-training these models. So for example, we might take a pre-trained model that is trained on public data, like scraped from the internet. Maybe we distill that model to make it fit on client devices, and then we use that as the initialization for our FL fine-tuning. And the reason for doing this is primarily one of efficiency and also model quality. So if you can pre-train your model, you require fewer federated rounds of training, which means you use up less privacy budget and you affect the quality of your model less. There's also, of course, computational advantages and communication advantages to do this. Now, in this work, we're going to think about an intermediate step here, which we're going to call pre-fine-tuning. So a number of papers have introduced this idea by different names. But the idea is that we take our pre-trained model, which was trained on kind of generic data, and we're going to fine-tune it on a still centrally held data set that is more relevant to our federated clients' data. So we're trying to push our model in the direction of the federated clients' data. And again, the reason here is so that we can do fewer rounds of federated training. And of course, the pipe dream here is maybe we can get rid of the federated training part altogether. So the question here then is, how do we actually choose this pre-fine-tuning data set? Where does it come from? And if we have multiple options, how do we pick one? So just to give you kind of a quick illustration, let's think about a scenario where we have test data, which is federated across multiple clients and consists of data from Stack Overflow. And on the other hand, and our pre-fine-tuning data is some mixture of our real clients' data, the Stack Overflow, with something else, in this case, Wikitext. And clearly, the best thing we could do here is to have a pre-fine-tuning data set that matches our test data. So ideally, we would like 100% Stack Overflow in our pre-fine-tuning. But it turns out you don't actually need that in order to reduce the impact of federated fine-tuning. So for example, just to put some, so this table is showing for different mixtures of our pre-fine-tuning data set, what is our test perplexity before FL fine-tuning and after FL fine-tuning. We want to know how much that gap is. So just to put some numbers on this, if your pre-fine-tuning data set is 70% similar to your test data set, FL fine-tuning here was giving only a 2% gain in test perplexity, which could be significant in certain scenarios, of course, but something to keep in mind. And this table was computed without DP. So once you add the noise of DP updates during federated fine-tuning, these gains from federated fine-tuning could get smaller or even disappear. So the key question then is, how do we acquire and find a pre-fine-tuning data set that is good enough that we can actually reduce how much FL fine-tuning we need to do? And here, there's been kind of an explosion over the last couple of years in sources of data that people could use for these purposes. One such source is data markets. So data marketplaces are places where vendors can put up data sets, sell them, and they're easily searchable by users. So AWS has one, Snowflake, DataRaid. And on these marketplaces, when a vendor lists a data set, so for example, here we see a data set of vessel ownership, I can see that this data set costs $7,000 to purchase. But I can also get a preview, a free sample preview of this data, from which I need to decide if I want to purchase this data or a different data set from a different vendor. Another example of places where I can get pre-fine-tuning data sets is from generative data vendors. So there's a lot of companies selling access to generative models. And before I purchase access to this generative model, I'm typically given a preview of some samples from that distribution. And from that preview, I need to decide whether I want to purchase access to the full data distribution. So these are two examples where basically we have different options for data, and we're given a small sample data set from which we need to decide which data provider we want to go with. So the natural question is, how should a data user pick between these data sets? We started looking at this question in the following problem setting. So we modeled this having n data vendors, each of whom has data drawn from a distribution P1 through Pn. And these distributions can be different in general. We assume these are heterogeneous distributions. And each of these distributions we can think of as having some inherent value to the end user, which we'll call epsilon of P. But this inherent value of the distribution isn't accessible to the data user. Instead, what they see is a sample data set that's drawn from this underlying distribution. So for now, let's assume that those draws are independent, or IID, from the actual data distribution. Of course, in practice, this could be done adversarially. So we have these sample data sets, and from these data sets, we're going to extract some data set valuation new. And that is what the data user is going to use to choose which vendor they want to purchase from. So the core question here is, how do we choose a distribution valuation function, epsilon, and a data set valuation nu, so that a data user can identify the best distribution with the highest epsilon from samples from the nu of D? Now, this problem, as stated, isn't well defined. The core is that we need to determine how to define this epsilon without knowing the downstream task. So to handle this issue, we use a Huber model of data heterogeneity, where we assume that there exists a reference distribution P star. So you can think of this as like the test distribution that the client is trying to match. And basically, each data provider has some contamination distribution, Q1 through Qn. And the actual distribution that they observe and that they draw their data from is going to be some mixture of their contamination distribution and the true reference. And different vendors can have different mixtures. And this reference gives us some point of reference with which to determine the quality of a particular distribution. So basically, the closer to the reference you are, the more valuable your distribution is. So the short version of this work, which is still in progress, is that if you use a distance measure epsilon that is based on the negative MMD, maximum mean discrepancy, and you use a known biased estimator of the MMD for your empirical nu of D, data set valuation, and you approximate your reference distribution P star with a union of all of the other vendors' data, then you can get a guarantee that looks something like the following. This is an informal statement, but let's start here at the bottom. Okay. So our buyer wants to know, is vendor I better than vendor J in the distribution sense by at least some amount rho? What they see is the data set valuations, nu of DEI and nu of DJ. We see that those are different by a quantity delta. Now, if delta is at least as big as this middle equation, then you can guarantee that with high probability. So what is delta? So delta depends on several terms. The first is the desired gap rho. Then we have a bias term based on the estimator, a previewed data set sample size, and a constant that depends only on the heterogeneity in the problem. And so the point here is that most vendors actually don't give large enough preview data sets to use this result meaningfully. So this tells us something about how to select data if we don't care about privacy. If we also want differential privacy, it gets more complicated. So actually the MMD estimator has a very high sensitivity. So the terms in red require a lot of noise to be added to get a DP estimate of MMD. So in a recent workshop paper, we looked at using instead the Frechet distance, which has a nice closed form solution for Gaussians and allows you to get low sensitivity estimates in a differentially private setting. And we found that this DP Frechet distance gives very good data set selection for pre-fine tuning. So to summarize, data set selection is becoming more important. In FL, this may manifest as pre-fine tuning. But I think there's a lot of interesting questions around how do we select pre-fine tuning data sets. So MMD, we've seen, allows for fine-grained data selection based on heterogeneous data distributions, and Frechet allows for differentially private selection. Can we get both? And downstream, can we potentially remove the need for FL fine-tuning by pre-fine tuning intelligently? Thank you.
Thank you so much, Giulia. We have time for like maybe 1 or 2 questions at most. Are there questions? Okay. Then I'll pass this to you.
I wanted to ask about the valuation that you mentioned, because as far as I could tell, that was kind of, for instance, the price on these sites that people are listing. But what happens if that is, let's say less than honest? How do you actually start to do this in an area where people are lying about the quality of their data?
Yeah, we've started thinking about that a little bit, but yeah, I think one knob that we have is to require or expect vendors to provide at least a certain amount of data. Okay, that's again assuming that they're not lying about data that they actually have. But let's say that they're taking samples from the data that they actually have accessible, but they're choosing that adversarially or strategically. The larger the data set you require them to provide, the harder it is to try to mimic a target distribution that they're trying to match. And I think there are some interesting questions around both modeling the adversary there and trying to figure out what kind of guarantees.
Okay, let's thank Giulia once more. Our next talk is by Kate Donahue. Kate is a PhD student at Cornell, and she's interested in algorithmic approaches to generally problems with potential of societal impact in AI. This includes fairness, distributed learning, and AI, human-AI collaboration. Take it away.
Thanks so much. So I'm Kate Donahue. I'm going to be presenting joint work with my advisor, Joan Kleinberg, on incentives and opportunities in model sharing games. So I'm going to start out with a motivating example. So imagine that I'm some hospital and I'm trying to build a model to predict patient outcomes. So one option I could use is I could just use my local data, my local patient data, and try and build some model based off of that. Problem is, I might not have that much data locally. This might give me relatively high error. So as everybody's been talking about, we could use federated learning or some other sort of collaborative learning setup to try and potentially do better. And one sort of important question is which of these two options is going to give the hospital lower error? And so if data is IID between hospitals, it's sort of a little bit clear a priori that federation is probably going to be better. Like all things being equal, there's more data. But as people have been talking about, like if the data distributions are not IAD, if there's truly different patient distributions, this isn't as natural. And so there are a lot of natural application areas, medical, we were thinking about this in early pandemic, so that was extremely relevant for us then, but a lot of other cases where this comes up. And one thing I really want to think about is this is especially interesting if we view federating agents as game theoretic players. And I think this makes sense in the hospital case, in this sort of cross-silo case. I think it's also worth considering in the case of this cross-device case, where maybe I can't actually, with my cell phone, I can't choose what I want to do. But I think it matters if I want to, right? If I'm dissatisfied to the point where I'd rather have some other option, or I'd rather not federate at all, it should be something that we should care about. And so if data is non-IAD, federating in this like grand coalition, everybody in one group, might not be optimal. Local learning might not be optimal. It might be that some other arrangement, like this thing here, like some other set of coalitions of federating players might be optimal for different notions of optimal. And the question I'm going to talk about is how do we reason about strategic incentives in model sharing games with non-IAD data? And so what do I mean by model sharing games? This is a framework John and I came up with. It's a definitely very simplified model, but I think it's expressive enough to get at a lot of interesting questions. Some features it has are there's varying numbers of samples per agent. So n sub I, like this cute example on the left, like different agents are contributing more or less data. There's some concept of the noise of the data and the noise of the learning task, and also bias between agents. So the average is similarity between agents. And this will be sort of a critical term that will influence sort of the stability and outcomes in a lot of settings. We also model varying federation methods, different notions of personalization. And the cost metric I'm going to consider mostly is the mean squared error for learning tasks. And we get exact results for linear regression and mean estimation. So some high-level questions I want to talk through super briefly is which federating arrangements are going to be stable, which arrangements are going to minimize societal cost, and which arrangements are going to be fair for different notions of fairness. I'll go through these pretty quickly. So stability. High-level results are we give conditions where local learning, federating in the grand coalition, or some other arrangement entirely might be stable. We mostly consider individual stability, which is basically no player wants to join a coalition that would welcome it. And also we consider a few other notions. Generally, our results depend on the size of the players, how much data they have, as well as this sort of noise bias parameter I mentioned previously. We consider different models of personalization, vanilla, as well as sort of fine-grained, which is basically a more personalized notion, allowing players to sort of very aggressively adapt their data. And as you might expect, more personalization always increases the sort of stability of the grand coalition. So stability, one question you might immediately think about, like how, if we're allowing players to self-arrange into different coalitions, is this going to be optimal? And if it's not optimal, how far from optimal will it be? And this is the next set of questions we thought about. So we looked at sort of weighted total error as an objective, a pretty standard objective in federated learning. The first thing we showed is that either local learning or the grand coalition could be arbitrarily far from optimal. So you really sort of can't do something sort of clean and obvious and get close to optimal. You have to be a little more sophisticated. We showed that there exists an efficient constructive algorithm that gets you sort of the optimal arrangement, that gets you from any sort of arbitrary arrangement to something that's optimal. And we use these results to give a price of anarchy bound of 9 in this setup. So the last thing you might think about is fairness. And this one was especially interesting. So we were looking at some of these related papers and saw that there were sort of at least 2 natural existing notions of fairness in the federated learning sphere. And I think both of them make sense in different contexts. So returning to this hospital example, imagine that I'm sort of a historically underfunded hospital. And I don't have that much data because I don't have that much money. And you might say like, okay, it seems fundamentally unfair that I would have higher error because of this. And maybe our notion of fairness is that we want to compensate for this and give me error rates that are roughly equal for everybody I'm federating with. Makes a lot of sense. There's another notion of fairness, which is proportional collaborative. And maybe in this setting, assume that I don't have that much data because I've just been lazy. I haven't been collecting that much data. Maybe I have adequate budget. And here a goal of fairness might be that I want to sort of punish me for this, and we want to have error rates be inversely proportional to data collected. I think this also makes sense in different settings. And there's been a series of works that have been trying to achieve both of these in different settings. In this work, we sort of compare each of these and give results for when they might be satisfied. And specifically for egalitarian, we show a tight bound on the ratio of errors between any 2 players federating together for a quite wide range of federating methods. Like it holds for a relatively large set of federating methods. For proportional and collaborative, we show that the story is more specific to the federation method. And specifically for the more personalized notion of federation, we show that a variance always holds. And for this vanilla notion of federation, it holds if it's individually rational, which is a kind of fun connection back to our first paper where you had this connection between stability and fairness. Like if you know that no player wants to leave for local learning, you automatically get this notion of fairness satisfied. So there's some ongoing work and things I've been thinking about. There's some questions about stability with differing known player types. Like suppose I know that I'm a red hospital. You could have some interesting questions about incentives, like would I rather federate with 2 red hospitals who are maybe more similar to me, or 3 blue hospitals who are more different from me? And how does this change? You have to have correct beliefs. How does this change the question of stability? There's also been some interesting work on competitive agents. So far, I've assumed all players are sort of selfish, but not competitive. Does this change the notion of stability? I think there's also interesting questions around LLM content generation, like what if the outcome of this federating learning is not a model, but it's a model that's going to be used to create more data? Does this change my incentives for participating? There's been some work that's sort of built on this model sharing games framework and sort of personalized collaboration, used it to explore questions around privacy and data valuations. There's also been a ton of really interesting related work in this space, things around sort of heterogeneous data, around personalization, clustering, work where you sort of cluster people who are similar and different, questions around how you do this when people have sort of different privacy preferences as well as different data, questions for how you incentivize people to collect more data, and how you incentivize them to be honest. Like so far I've assumed people are sort of honest, but what if they're allowed to lie? How do you make sure they don't lie? And questions about different fairness. So yeah, this is high-level summary. Thank you guys so much.
Thank you so much. Questions?
Yeah.
The notions of fairness that you talked about, first of all, really nice line of work. But one thing I had a question about with the fairness, it seems like you might also want this to depend on the quality of data. Like maybe you collect a small amount of data, but it's very, high quality or something like that. Is that taken into account in the current work, or would there be an easy way to address that?
That's a great question. So you can sort of view data quality as similar to data quantity, where basically if you could scale up and down in the error form we have, that sort of immediately influences your term of quality. There's a model that's that's the high level, like you can get that roughly. We have sort of a more sophisticated way of modeling that's actually in part of this ongoing work, where we have a version that allows for different quality.
Okay.
So two-part answer, partially answered, but more interesting work ongoing. But yeah, great question.
Cool, thanks.
We have time for one more question. Okay, I'll ask one while Praneeth is setting up. It was really interesting to see that towards the end you started talking about choosing your collaborator, like the red and blue. In general, I was thinking, what are your thoughts about the role of partial information about your own type and others' types and attitude towards collaboration?
That's a great question. That's a great question. So I think that's the thing that sort of tripped us, or the question that was worth thinking about, where it's like, I need to know my own type. I need to sort of have accurate information about this. And something that sort of was tricky for a while to think about is like, if I know my own type and I know you're the person's type, why don't I just subtract off the difference and then we're not in the question of different data? And so you need to be in this particular data set, this situation where like, I know your type, but I can't exactly compensate for that, which I think does exist in some settings. But it's sort of an interesting set of things to think about, a set of circumstances. Did that address your question, or were there more things?
Mostly. I think this is like, we should discuss
we should
it further after.
Yeah. No, definitely. Sweet. Thanks so much.
Okay, thank you so much, Kate. Okay, so our next speaker is Praneeth Karimireddy. Praneeth is a postdoc at UC Berkeley, and he got his PhD from EPFL. He is interested in his research in, I feel like, all aspects of the infrastructure for collaborative learning, from the generation of data to the usage of it to the governance of it. So we're looking forward to it.
Thank you so much for the invitation. So this is going to be more of an overview kind of a thing. Thankfully, a lot of the speakers before have set up a lot of the things for this, so I can be super high level. I'm hoping to spark more discussion, so it'll be a little light on the technical details. Okay, so the main takeaway I would hope you guys to have from this is, if you want to think about incentives in federated learning, or if you want to think about data markets and these kind of questions, experiment design is probably where you want to look. It offers like a lot of tools from statistics to think about these kind of questions. So hopefully I'll convince you of this and the rest. Okay, so what do I mean by a data market? I really think we should think of federated learning as a data market. By this, I mean that there's a platform designer who designs the platform to achieve some goals. And that there are, we should really think of the, as Kate was saying, we should think of the participants, the data contributors, as really as agents who have some agency. So the figure doesn't matter too much, but the one thing which changes from the standard federated learning setup where people just upload the data and get a model, the one thing we change is we allow the participants to have autonomy. So this was pointed out by Katrina that so we really need to give the agents autonomy to decide on what data to collect, what data to share into the system. So what would a system which allows this look like? From the perspective of the agent, the system, what are the agent's goals? So potentially they have a question they want answered. That's the whole reason they're participating in the system. This can be a prediction task, right? And they have some payment they use to, so this can either be a cash, which is like a standard marketplace, but it can also, they can also pay with their own efforts, with their own data collection. And in return, they buy a reduction in uncertainty on their answer. This is the fundamental transaction which is going on. So you pay either with cash or with your own data, and you buy a reduction in uncertainty. So this fundamentally places uncertainty and quantification of uncertainty at like the central role in all of this. Just to formalize this setup a little bit. So suppose there are 3 agents. So I am on the left, and I'm trying to see, so I have some data set. So I also have a question, which is prediction on this X test. I give my payment, which is this my data set, and return through some magic of federated learning, I get a model trained. And with this model, I get my predictions. So was this, how useful was this entire process for me? To be able to quantify this, we need to somehow measure the quality of these predictions. So an obvious way may be, okay, we can just use some held out test data to estimate this quality and to estimate this uncertainty. Let's put a pin in that. So first of all, we might not have labeled test data, but okay, suppose we do, but and we can use this. Let's put a pin in like using test data to estimate this uncertainty for now. How does the data market look from a platform perspective? From the platform designer wants to attract a lot of participants. They want efficiency. They want to make most use of the data which has been collected on the platform. And they want to collect loads of useful data. So this is probably the goals. Maybe they have some more, but they essentially want to shape the decisions made by the agent. So that's the goal of the platform. So these decisions can be, so what are the agents can try to decide, is it worth it? So I gain some reduction in my uncertainty, but I have a cost which I have to pay. Is it worth it on the whole? So this is a decision which the agent makes. So this is called individual rationality in the literature. Another decision the agent can make is it's now a marketplace. So if I have to maximize what I'm getting, if I've strategically decide what data to collect, what data should I collect to maximize my reward? Now, so clearly to answer any of these questions, we would need to quantify uncertainty. We would need a way to estimate uncertainty to make any of these decisions. And that's now, let's get back to that pin where we said, let's use test data to estimate this uncertainty. The issue is we cannot. And the issue is that any estimate we come up with this test data set will influence the agent's decisions. So you have this setting where you're using the test data, creating some uncertainty estimates, but these estimates are then influencing the decisions made by the agent, and so are influencing the data set collected. So this is like a classic problem in statistics, that this inference after data selection. So the estimate is no longer valid. So any kind of uncertain estimate which relies on test data is not useful. So this is like a fundamental problem. I think this is the problem in figuring out all of these data marketplaces or incentives. And so what's the solution? Okay, first, let's start with something extremely simple. Let's just assume data is IID. So then we can just use standard generalization bounds. We have a lot of theory in generalization bounds. So we can just use that to estimate uncertainty. And then more data just means lower uncertainty, and it's a neat, clean solution. So we did some initial preliminary work on exploring just the setting, and the setting itself has some pretty interesting results. So what we were able to show is that if you model all of these properly, the standard federated learning framework suffers catastrophic free riding. But there is a simple fix to it, like this kind of the kind of solutions which Kate alluded to, where you shape the reward which is given is proportional to the effort you put in. If you do something like that, you can prevent free riding, you can ensure efficiency, and you can prove that it is optimal, which means that the maximum amount of data is collected by the platform. There's more results which I won't get into. But this is severely limiting the idea that you have to assume IID, and the idea that you have to rely on these loose generalization bounds to do anything is pretty limiting. So we were thinking about how to go beyond this, and the concrete use case we were thinking about is clinical trials which are done across multiple hospitals. So in such a setting, you have, say, X here represents some demographics about the patient. The theta star represents the whatever ground truth efficacy of the drug you're testing. And the Y represents the outcomes. And usually you assume that it's a linear model. So inside a setting, suppose there are multiple possible patients you could recruit into your trial. These patients are spread across the country. So across, there's different demographics in this. Each agent is a hospital which is geographically located in some area. So they care only about a subset of these demographics, which is most pertinent to them. So each agent only has access to a subset and only cares about a subset. So each hospital will on their own choose which patients to recruit, so which data sets to collect, how many to collect, and what to share. So they are making the decisions based on their own best interests. So in such a framework, so we look at this framework, but we restrict ourselves to this linear setting. The nice thing about this linear setting is that you can quantify uncertainty very, very concretely. So suppose I have some training data, say this TR represents the training data. The uncertainty along a new direction X has this nice closed form solution, which I can write down. This does not read any sort of assumptions on what my training data is, and it does not need any assumption on how the test point X relates to the training data. This comes from like standard experiment design stuff. And it does not even require labels, training labels to compute this. So we can use this, fundamentally we use this, which is basically experiment design framework, to design a mechanism around it. You can create a market around it. So there's some results we have. I won't go into the details, but the upshot is that there's many different criteria people use in statistics for this for doing this experiment design. We show that only one of them is actually incentive compatible. So this has pretty strong implications for running fair clinical trials. And also that so there's a fundamental trade-off between efficiency and fairness. If you want to prioritize efficiency, you have to sacrifice fairness. So we show this dichotomy. So if you care about efficiency, there's a nice algorithm which works. And if you care about fairness, or you care about this optimality in terms of maximizing the quantity and the diversity of data collected, there's also a mechanism which achieves that. Again, more results in the paper. This is just like a simple plot to show that this actually works. The dark ones in the top are the baselines, and the light ones at the bottom are us. So this is like a huge difference in this. Yeah, so also talk to me about, just wrapping up now, also talk to me about applications. A lot of these questions really came from talking to people in the applied folk, like and NGOs who really grapple with these privacy and autonomy questions, algorithms and mechanisms like what Katrina was asking before, like this collective data governance. Thank you.
Thank you so much for the talk. We have time for one short question while Zachary sets up.
Thanks. So here you focused on the agent wanting to get something out of the interaction. And I'm curious though, in the other direction, maybe it's the server that's wants, or the controlling entity that wants to, and what the agent maybe wants to get is just money or some other form of side payment. Does that? I'm just wondering how that fits in this framework.
Absolutely. It's not just, so the agents have autonomy, they have goals, but of course the principal also has goals. The principal wants to maximize the amount of data collected. Maybe they want to maximize the amount of money collected. So this framework requires both.
I guess I'm more thinking of like the where the agent does not, so here the motivation for the agent was actually improving their predictions. But
Yes.
I'm thinking of the setting where the agent actually doesn't gain anything from, or not significant. Whereas, and so the principal might make a side payment to make in order to satisfy a.
That's an excellent question. I haven't worked on that version of the problem, but I'm pretty sure most of the technical stuff here can be translated.
Okay, thanks again, Praneeth. Our next speaker is Zachary Charles. He's a research scientist at Google, and he's, of course, worked on federated and collaborative learning and distributed learning with a special focus on efficiency and practicality of their methods.
Okay, wait. Is this something? Yeah, sorry. Okay, great. How much time do I have? Can I take the full 10 minutes or should I? Okay, cool. I'll try to be a little bit fast though. This is called Towards Federated Foundation Models, and this is really envisioning what would it take to get to a point where we could actually train foundation models and LLMs using federated learning, and specifically, how do we enable the research that would be necessary for that? So there's kind of multiple stages, and we're kind of at stage 0. This is joint work with a bunch of my great colleagues, one of which is in the audience over there, Krishna. So I don't have to dwell on this. People have already made this distinction. There's kind of federated data where you have the data is coupled to the device it's in, or maybe the silo that it's in. And there's kind of group structured or collaborative data, which is just that the data has some notion of partition. The data is grouped according to something. And this encompasses a lot of things like federated learning, meta learning, personalization, user level privacy, and a bunch of other things. So I'm going to de-emphasize data location and just focus on the group structure of the data. So why might we want research on LLMs and FL? A really non-exhaustive list. I bet you come up with a bunch of other things if you wanted. One is user level privacy. This is, to me, one of the most important. FL is basically one of the most promising ways to enable user level privacy right now. There are other alternatives, and I think they're worth considering, but there's been a lot of traction in terms of user level DP that we should imagine. And we should imagine what would it take to have, for instance, a foundation model that had user level DP baked in from the beginning. FL training might improve downstream applications. If we want personalized LLMs, why don't we train on relevant data instead of some random pre-training corpus that has no bearing on what you're actually trying to do? LLM stuff already exhibits group structure too, right? All these benchmarks are group structured data. They have 20 different tasks and they evaluate on each of them. And why does our training ignore this? Largely, there is some stuff that kind of encompasses this, but it's not really one-to-one. So to me, it's very, very exciting to think about how should we actually do LLMs with group structured data. What do we need for this kind of research? So the point I want to make is that foundation models were essentially enabled by a combination of research and engineering, and that I don't think you can divorce the two. They really, really reinforced one another. And this is a bunch of papers that really combined all of these. It was also aided by the curation of really large-scale data sets. This, I think, is a thornier section. I want to maybe say that there are issues with things like data consent and copyright and a bunch of other things. And so I think we want something like this to enable, work on, let's say, collaborative learning and LLMs. But we both have to take inspiration from and maybe some critical lessons from these kinds of work. And what did they do well? What did they not do well? How do we adapt it to the settings that we actually care about? So going to put that as like kind of a big caveat. Yeah. So what do we actually need for research on LLMs and FL? These are my personal opinions. They don't necessarily reflect everybody in this audience. And I think that you should push back if you feel that they aren't, true. But one of the things that I really, really care about, research in FL right now, the #1 complaint that I hear from people is that there just are not a lot of relevant data sets that people can use. This is kind of part of federated learning, right? The data doesn't leave the device, so nobody has the data to make available for research. So this is kind of a quagmire. And one of the things I really want to maybe say while I have a podium here is that EMNIST and CIFAR can only go so far. So yeah. We want explorations of how FL works at larger data set and model scales. Small models and large models behave differently. There's a lot of work showing this. And so maybe it's just a question for the audience. Is client drift still a relevant phenomenon at LLM scale? I'm not actually sure. We want FL work that prioritizes research and engineering. I think you need both, and doing them separately just encourages divergence. And also more collaboration and coordination. Our collaborations should probably mirror the ethos of federated learning. And when you look at some of the work on these 2 slides, they tend to be dominated by single institutions. And so maybe that's a bug in the system. Maybe if we actually care about things like learning across collaborative sources, our research should reflect that. I am just as guilty of that as anybody else. So I will say that I'm a hypocrite up here, but yeah. Okay, some work that we've actually been doing that are 2 very, very, very small steps towards this. Essentially 2 things. One is an open source library we're calling Dataset Grouper. This is essentially to help remedy or at least mitigate the issue of making data that is relevant for FL research available to academics and industry researchers. It's essentially a way to create scalable group structured data sets that you can use in your simulations. It's on GitHub right now, open source. Please file issues, bugs. I monitor it. So I'm very, very excited about this. I'll talk a little bit more about what it does. And in that, and in a forthcoming paper, we actually have some FL simulations at the scale of GPT-2, which were enabled by this dataset library. So dataset grouper is intended to be kind of a flexible way to partition existing datasets. So grab your favorite dataset from, let's say, TensorFlow datasets or Hugging Face. Say how you want to partition it across clients, and just go. It's supposed to be scalable. There's a caveat there, which is compute. That's always the caveat. But regardless, we were able to use it to get kind of new large-scale federated text data sets that are essentially orders of magnitude larger than other data sets in the literature. In particular, we have a federated version of the C4 data set, which has 15 million groups in it and billions of words. And this is what we use for our simulations. It is platform agnostic. It'll work with anything that uses TensorFlow, PyTorch, JAX, or NumPy. This is a part where I see this as really important. And the simulation ecosystem in FL right now is very fragmented, and that's unfortunate. So this is just some statistics of kind of ways in which these data sets are larger than previous data sets. May or may not be useful to you. But with this, we were able to do kind of larger scale FL simulations. Still not large scale, still not like billions of parameters or anything like that. But we were able to train a 108 million parameter transformer model on federated C4 from scratch. We did federated averaging, federated SGD, 16 clients per round, 64 batches per client, which is a really, really relevant number because it means that you're doing lots and lots of local training at every communication round. We did 2 kind of evaluation mechanisms. We took clients from the Fed book corpus open dataset, which is different from federated C4, so it's kind of slight distribution shift. We measured the pre-personalization performance and post-personalization performance. So how well did you just do with the global model, and how well did you do after local training? And we found the results somewhat surprising. Maybe somebody in the audience already has an explanation for this. I know there has been some theoretical work in terms of, let's say, 2-layer models or linear models or things like that. But federated averaging did not do well in a pre-personalization sense. It acted more as a meta-learning method. It essentially was able to adjust more quickly to these new distributions as opposed to learning a model that did well across all clients. Unfortunately, timing didn't work out. The full paper is going to be on archive tomorrow, if you're interested. If you want to check it out today, let me know. I'll send you a preprint. But yeah, so with that, this is only the tiniest step. There's a lot of things that we need. We need practical training strategies, group level DP at scale, group level fine tuning. What does that look like? Group level reinforcement learning with human feedback, scaling laws, architecture development, fairness and ethics studies, benchmarking, like all these things are really, really important and are essentially absent. So I'm interested in them. If you are too, please reach out. Okay.
Thank you so much for the talk. We have time for 1, maybe 2 questions.
questions?
So first of all, I really like the focus on groups. I think to Katrina's point earlier, it points out that in federated learning, this idea of heterogeneity goes way beyond federated learning, in fact. Yep. And so I can imagine this being very useful for any time you're trying to learn over heterogeneous data. The thing that I was curious about, though, is it seems like with group structured data, part of it would be, it'd be important to think about how the data is being generated in these different groups. So do you have ways, when you have these tools for partitioning the data, how are you thinking about heterogeneity as part of that? Like, is it, are you randomly partitioning? Are you trying to do some sort of, different sampling scheme, or how have you guys thought about that?
So there's lots of things you can do. We've only scratched the surface. You could do randomly partitioning. We didn't actually do that. We did something with C4 where we, every example in it has an associated URL. You can extract the base domain from that, and we use that as our partition function. This is arguable as to whether it's useful or not, but it did form some semblance of groups that was, to me, interesting at least. I have a lot of questions about this too, though.
So I have another question. What type of devices do you think you're going to train these things on?
I think this is a good question, and one that I don't have the answer to. A lot of people are working on putting foundation models on device right now, and I don't know what the progress is going to be in 3 years. That's where my mind is at. In 3 years or in 5 years, what are we going to be able to do on device? And let's anticipate it and meet them there instead of reacting to it. So I don't have a great answer for you. And this is part of the reason that I really, really like the emphasis on collaborative learning, group structured learning that's kind of pervaded a lot of the other talks today.
Okay, thank you so much for the talk. Let's thank all the speakers in this session again. We're going to take a short break, but before we do that, Virginia has an announcement.
Oh, yeah. So I think maybe we can come back at 11:20. So that'll be about, not the full 15 minutes that we were hoping for, but 12-ish minutes. So a little time for a break. We also wanted to just, I think there's not too many additional folks beyond the invited participants. So if folks want to stay around for the discussion session that's happening, there's 2 discussion sessions that are happening today, please feel free to do so. So we'd be happy to, expand it to this a slightly larger group of folks that are here today. Yeah, so that's all. So let's plan to meet back at 11:20. Folks who want to stay for the first discussion session. So this discussion session, by the way, there's a few key topics that I'm hoping we can talk about today. This is partially just as a way to spark some discussion, but also for this very concrete goal of writing a white paper that talks about some open theoretical directions in federated and collaborative learning. So the first sort of discussion topic that I want to talk about, and I thought we could talk about for this first session, is basically what are the major directions we'd want to talk about in the space of federated and collaborative learning, the major open directions. And this is useful both as a way of starting the discussion about what we mean by these broad terms and the field generally, but it's also concretely very useful because they will be sections of the eventual paper and they'll form the working groups that we can join tomorrow. So I have a couple more thoughts on that I'll introduce at the beginning of the discussion session, but let's take a break. So we can come back in 10-ish minutes at 11:20.